Hello, let's begin one more lecture session on infinite series. Now, in the last session, we had started discussing tests of convergence for positive series. Last class, actually, we had discussed the comparison test, and for today, we have the next test on the line, that is the D'Alembert's ratio test. So, what is that? This test says that if sigma un is a series of positive terms such that limit un plus 1 by un n tends to infinity is equal to L, then this series is convergent if L is less than 1, divergent if L is greater than 1, and the test fails if L is equal to 1. Now, note one thing over here. In the comparison test, actually we had to choose a second series for the purpose of comparison with the given series, and based on that we used to give the conclusion that whether the given series is convergent or divergent. However, in this case the things are much easier because we don't need to choose any second series. What we are comparing is the two consecutive terms of the same series, un and un plus 1. So we just take the ratio and take the limit, and depending on the value of the limit, we get our decision as whether the series is convergent or divergent. And note that this test cannot give any conclusion if L is equal to 1. Okay, so let us now look into problems to use the ratio test and get our conclusion about whether a given series is convergent or not. So the first problem here is examine the convergence of the series summation n equal to 1 to infinity n to the power n by factorial n. So what is our un over here? Our un is obviously n to the power n by factorial n. And then un plus 1 will be given by n plus 1 to the power n plus 1 divided by factorial n plus 1. So we are simply replacing n by n plus 1 to get this un plus 1. And now let us form the ratio and take the limit. So limit n tends to infinity, un plus 1 by un. This is limit n tends to infinity, n plus 1 to the power n plus 1 by factorial n plus 1. And our un is n to the power n by factorial n. So it gives us multiplied with factorial n by n to the power n. Now we need to simplify this term over here. Now notice that this factorial n we can cancel with factorial n plus 1 and we will be left with only n plus 1. That n plus 1 can again be cancelled with this term in the numerator, and finally we will be left with n plus 1 by n to the power n. So that is actually 1 plus 1 by n to the power n. And can we recognize this? This is a standard limit, and we know that the value of this limit is e. And of course, e is greater than 1. So by ratio test, we can conclude that the given series is divergent. One more example, let us see. So test the convergence of the series 1 plus 2 by 2 cube, 1 plus 2 plus 3 by 3 cube, 1 plus 2 plus 3 plus 4 by 4 cube, and so on. So what is the nth term or un over here? See that the nth term will be 1 plus 2 plus 3 up to n plus 1, because the third term is going up to 4. And the denominator here is 4 cube. So in the general term, it's n plus 1 whole cube. And we can add this, right? So what is this sum? This is obviously n plus 1, n plus 2 by 2, using our formula for adding natural numbers. So now with a little bit of simplification, we get this is equal to n plus 2 by 2 n plus 1 whole square. And now we can write un plus 1 just by replacing n by n plus 1. So this becomes n plus 3 divided by 2 n plus 2 whole square. So now we form the ratio and get the limit. So limit n tends to infinity un plus 1 by un. So here we have just put the expressions for your un plus 1 and un, and we need to simplify. Of course, 2 over here cancels out from the numerator and the denominator. And from the numerator, if we take out n term from this and n square from this, similarly again from the denominator, what we get is 1 plus 3 by n, 1 plus 1 by n whole square, 1 plus 2 by n whole cube. And now as we take the limit as n tends to infinity, what happens? You see that these terms 3 by n, 1 by n, 2 by n, they all become 0. So finally the value of the limit is 1. So that is a problem now, isn't it? Because for the limit 1, the ratio test fails. So then what is the way out? What can we do? So obviously we have to use some other test. And we still now have learned only the comparison test. So let us try to use the comparison test. Let us choose the second series of the comparison test, Vn, as 1 by n. Now see, limit un by vn as n tends to infinity, as we put the values of un and vn over here, takes this form. And now again, if we take out n square from the numerator as well as from the denominator, we will get in the numerator 1 plus 2 by n and denominator 2 multiplied with 1 plus 1 by n whole square. So now as n tends to infinity, of course 2 by n goes to 0, 1 by n goes to 0. So the value of the limit is half a finite number. So now we can use the comparison test to compare un and vn. And see, what is the vn actually? This vn was 1 by n. So this is actually nothing but the harmonic series, which we know to be divergent. So therefore, by comparison test, we can see that the given series is also divergent. So let us take up one more problem. Test the convergence of the series 1 plus x by 2 plus x squared by 5 plus x cubed by 10 plus and so on. Now notice one thing here, each term contains some x. So this kind of series is actually called power series, which contains actually powers of x. So now what is the un over here? How can we identify un? We can write un as x to the power n. You see here we have x, x square, x cube. And this term can be of course assumed as x to the power 0. So we are starting here from n equal to 0. And we write un as x to the power n divided by n square plus 1. Then un plus 1 will take the form x to the power n plus 1 divided by n plus 1 whole square plus 1. Now as usual, we will form the ratio and then take the limit. So limit n tends to infinity, un plus 1, this is x n plus 1 and the denominator is actually n square plus 2n plus 2 multiplied with, from un we get n square plus 1 by x to the power n. So as we simplify this term, see that we are left with a x, and if we take out n square from both the numerator and the denominator, numerator is 1 plus 1 by n square and denominator is 1 plus 2 by n plus 2 by n square. So as we take the limit n tends to infinity, this term becomes 1. So finally the limit is x. So what can we conclude now by the ratio test? By the ratio test, this series will be convergent if x is less than 1, divergent if x is greater than 1. And of course, the test fails if x is equal to 1, right? So for x equal to 1, we have to think something else. So we have to use again comparison test for x equal to 1. Now note that for x equal to 1, the un term is just 1 by n square plus 1. And also observe that we can write this 1 by n square plus 1 is obviously less than 1 by n square, right? So if we choose our second series Vn as 1 by n square, we would be able to tell that un is less than Vn. And what is Vn? Vn is the P series with P equal to 2, isn't it? And this is known to be convergent. So therefore, by comparison test, if the bigger series is convergent, we can say that the smaller series is also convergent. That means our given series is convergent for x equal to 1. Okay, so with this example, we will close today's session. In the next session, we will take up one more test of convergence, which will be Cauchy's root test. Thank you.